Okay, I want to start off just by reiterating the key messages from last time, from Should We Trust Computers? What we discussed then was that most software has got more than 10 defects in every 1,000 lines of code, that many systems, many important systems now, are more than 1 million lines of code, which is a lot of defects, that testing software can only find a tiny fraction of those errors, and usually the most common ones, with the consequence that testing leaves a lot of relatively obscure errors. And that's why most software works reasonably well enough, but there are still too many failures, and software is easy to cyber attack, as quite a lot of incidents recently have shown. So that's where we got to last time. What I want to do this time is to give a very brief and partial, in both senses, history of computing to set a context for the kind of things that I'm going to need to draw on later in this lecture series. In particular, I want to answer the question, how did we manage to get from slide rules to driverless cars in less than a lifetime? And why is it that most hardware is extremely well engineered and reliable, and most software is not particularly well engineered, or not even really engineered at all, and contains a lot of defects, as we've just seen? And inevitably, because it's a big and very rich history with lots of interesting stories, I'm going to have to go fast, and I will leave out an enormous amount. A lot of the things that I leave out or only touch on, I will expand and develop in later lectures. So this is not the only chance, for example, to talk about formal methods. I will be coming back to mathematically formal development methods in a later lecture and giving some demonstrations of just what can be achieved that way. But inevitably, I have to leave out a lot. There'll be a number of people in the audience who've lived through a lot of this history and have their own stories to tell. Please tell them on the website so that we can capture them and share them. That will be extremely useful. If you happen to be in the audience and I've failed to mention your seminal contribution, or I've given it the wrong level of emphasis, or you were there and I get something wrong, then forgive me. It's terribly easy to do. Mechanical calculators have been around for a long time. Here's a few. In the early 20th century, electronic circuits started to replace mechanical calculators, and then Alan Turing came along and started doing some of the mathematics of computation. And of course, Turing's well known for his code-breaking work at Bletchley, but his contribution to computing is actually much more important than that. The thing I want to pull out is that his work on computability and his development, his demonstration that a very simple machine with a memory and a very limited instruction set could perform all possible calculations, that coming together with the electronic circuitry that could do calculations actually set the groundwork for the universal electronic computer. And that was the starting gun, really. And an electronic computer, as any kind of universal computer, needs a memory. Even Ada Lovelace knew that. And if you've been watching the adverts, you'll see we've got an Electron Babbage and the extraordinary Ada Lovelace coming up just next week here. But developing an electronic memory is actually quite a challenge. And Freddie Williams and Tom Kilburn were working on radar in the end of the Second World War and thought about the fact that radar screens, cathode ray tubes, fade slowly. The image on a screen disappears over a period of a second or three. And therefore, if you could read off the screen what was there, and feed it back round a circuit and regenerate the bits of it you needed to keep, then you would have an electronic memory that was capable of working at electronic speeds. And that's exactly what they did. They developed a pickup plate that would go on the front and the appropriate circuitry to do the regeneration. And when Kilburn and Williams went back to Manchester University, they built a machine to see whether that would work. And that machine was the small-scale experimental machine, became known as the Manchester Baby, built primarily to see whether the storage tube would work as a memory device for a computer. The computer was, I mean, most of that's power supplies, of course. That's the way with electronics. You get a huge amount of very impressive-looking power supplies. About 500 thermionic valves there, and presumably some air conditioning, because it must have got jolly hot. It only had 7 instructions in its instruction set. It could do 7 different things. And one of those instructions was stop. And its total memory on the storage tube was just 32 words of 32 binary digits, 32 bits. That was all the memory it had got, plus a one-word accumulator and another storage tube that simply kept the address of the next instruction in the memory, in the main storage tube. And it had a display, which you could select to look at any of the individual storage tubes and would normally be set to look at the memory. So you'd see the memory changing as the program actually executed. And the programs were held in that tiny memory and had to be entered through the switches on the front panel, in binary, of course, a bit at a time. But it was the first stored program computer, the first computer that actually had its program in the main store, executing, therefore, at electronic speeds and capable of being modified. So we had a universal computer running at that kind of speed. And Freddie Williams recalled the day when the first program ran. It must have been a phenomenal moment in the history of computing, because the start switch was pressed, and of course the spots on the display tube, as he says, it entered a mad dance, because that was the memory changing, those individual dots being rewritten and changing as the program executed. And mostly it failed until finally they managed to sort out what they'd got wrong, and the program worked. And there, for the first time, shining brightly in the expected place, was the expected answer. And as he says, it was a moment to remember. It was June 1948, and nothing was ever the same again. And nothing was ever the same again. That really, really was the point at which the modern computing age started. And things moved quickly. The UK government actually told Ferranti in a memorable instruction, probably the shortest contract that has ever been given by government to a commercial organisation, as you can see. And that was just in October, really quick movement after the success in June. And the Ferranti Mark I was completed in 1951. Manchester carried on doing research at a great pace. They had filed 81 patents by the end of 1956. Meanwhile, over in Cambridge, Maurice Wilkes was hard at work, also building a computer. And Wilkes' ambition was to build a computer in order to experience what it would be like to actually do real work on a computer. So he was out to produce something that was reliable, that was easy to use, that actually gave the opportunity to do some programming and find out what programming really was going to be like in the real world of computing. It had integral input-output, no more fiddling around with binary switches on the front panel in order to enter your programs, paper-tape input. It used mercury delay lines for memory, not storage tubes. It had been discovered that if you sent a pulse, essentially a sound wave, down a tube of mercury, because mercury is so dense, it goes very slowly, so you can get a lot of pulses into a tube. And if you've got effectively a microphone at the other end, you can pick them up again when they finally get there, and then your circuitry can regenerate them. So you can actually use the pulses going down a mercury tube as a memory. And it turns out to be very practical and very successful if you don't mind having half a ton of mercury sitting around in tubes in your computer. And mercury delay lines were used in practical computers for a good decade after that. So that was Wilkes EDSAC. And by 1953, EDSAC had been turned into Leo. Lyons bakery and café chain had been looking for ways to improve their business. They'd actually gone off to America to look for good new business ideas and had heard about computers and discovered that one was being built in Cambridge, just down the road from them. And they came back and they looked at it and they thought, yeah, that's what we need to do in order to make our business more efficient. And they hired John Pinkerton, a PhD student who turned out to be a brilliant engineer. And John Pinkerton turned EDSAC into the world's first business computer. And some people who I will mention shortly wrote the appropriate software. And it was such a success. By 1953, it was actually running the payroll for this organisation. And shortly after that, it was doing all the scheduling for the bakery as well and doing a lot of other office functions. Leo is Lyons Electronic Office, the acronym. And it was such a success that Lyons Bakeries founded a computer company, Leo Computers Limited, and started building computers and selling them to other companies. But the UK government didn't understand the potential of what had happened, of what they'd got in terms of the patents that were now held, in terms of the opportunities that opened up. And of course, money was very short. This was directly after the war. This rationing hadn't completely finished yet. This was a time when there wasn't a lot of spare cash around. In 1949, the Treasury came up with £15,000 to pay English Electric to work with the National Physical Laboratory in order to develop a computer that Alan Turing had designed. He'd actually designed it back in 1946, complete with all the circuit diagrams and an estimate that it could be built for £10,000. And they got on with it and actually successfully produced Turing's automatic computing engine called ACE. And that went on again to be a successful range of computers. ACE turned into Deuce and became a marketable product, and many of them were sold. But the government chief scientist at the time, when writing to the Treasury to ask for the annual contract to be renewed, observed that although there were a lot of computer R&D going on around various government and university centres, these machines were so powerful that he couldn't see that more than a few of them would be needed in the entire country. And I think, looking back, I think the government's focus at that time was that they saw these machines as scientific calculating machines, primarily of use to the people who were doing the atomic weapons development, because this was the time when Britain was running to develop the hydrogen bomb, because it was necessary in order to be able to persuade the Americans to share their atomic secrets. And so there was a terrific strategic pressure on actually developing hydrogen bomb weapons from the nuclear industry work that had gone on. But the age of computing had really arrived by this stage. And the US government certainly recognised the potential. They gave IBM $350 million as a military contract to develop computers, which of course completely dwarfed the amount of money that the UK government was spending. And at the same time, many other groups were working on computing, developing computers. It was a time when things were really buzzing in hardware development in the UK, in America, and elsewhere. There's a list here of the university groups and companies that were working on, probably not a complete list. The work at Birkbeck was, in my view, particularly notable because they did some of the early development of magnetic storage devices, of rotating magnetic storage devices. Kathleen Booth really is credited with developing the floppy disk, for example. They did a lot of development of drum storage and built computers and then moved those again out into commercial development. The hardware engineers, they had the benefit that there was a lot of physics going on at the time, and the physical processes for building the underlying components were getting better at a rapid rate. Transistors replaced thermionic valves. Manchester University had actually built a transistor-based computer as early as 1953 and got that working successfully. And that was obviously a big advantage because you gained speed, but you also saved a lot of power and a lot of heat generation. As I say, magnetic drum storage replaced things like mercury delay lines and storage tubes. Core storage was developed, little ferrite rings threaded onto wires that could be magnetized and polarized and then read back. And the development of transistors moved from discrete components into integrated circuits, several transistors on a single chip, and then into large-scale integration with hundreds and thousands of components on a chip, and then into very large-scale integration, packing more and more components onto a chip. The number of components you could get onto a single silicon chip was doubling every year. And that led to explosive growth in computing power at a stable price, at whatever unit price you chose. In a year, 18 months' time, you get twice as much storage, twice as much processing power for the same amount of money. And as the level of integration got higher, reworking the designs became more and more expensive. And therefore, the hardware engineers became very focused on getting things right first time. And much of the commercial driver went into really making sure that the engineering was better and better and better. Gordon Moore, who was a founder of Fairchild Semiconductors and then moved on to be technical director at Intel, wrote a seminal paper in 1965 called Cramming More Components onto Integrated Circuits, where, and this is a graph, figure 3 out of his paper, where he observed that this doubling was occurring every year and forecast that it would continue to happen for many years into the future. And he was right. That's another graph, but again with a right-hand scale that is a logarithmic scale, showing the development of the Intel family of processors. So again, a straight line in a linear logarithmic graph is an exponential growth. And you can see the number of transistors growing from 1,000 right up to a billion and 10 billion on a single chip. A quite phenomenal development of the hardware. This is Moore's law. This is what drove the spread of computing into a very, very wide range of applications. And I'll come back to that, but it's just worth thinking that vast increase in power going on year after year after year was revolutionary. In most industries, a factor of 10 change in the fundamental cost effectiveness of your core technology is revolutionary. We were getting revolutions every small number of years. And that meant that the software industry was having to run very, very hard to keep up with the new opportunities that were being opened up. And that's a key message from this history, and one that I will come back to. So what about software? Well, right at the beginning, it was machine language. It was the binary instructions that the electronic hardware understood. And then, because writing binary was slow and error-prone, the instructions were given mnemonics, easier to write things. You got a symbolic assembly language. You got loaders, little programs that were able to interpret the assembly language, turn it back into the binary and lay out the program in store. And those loaders grew into operating systems. EDSAC, because it was focused on making computers easy to use, actually came with subroutines. And David Wheeler had invented the whole notion of a subroutine right in the early days of EDSAC. And the Leo software was really the first business application software, a quite remarkable achievement back in the early 1950s. A team led by David Kamina, I have no idea if I've pronounced his name right, with Mary Coombs and Frank Land as part of that programming team. I think Frank Land, is still around. I mean, he may even be in the hall tonight for all I know. If he is, I look forward to speaking to him afterwards, because it was a phenomenal achievement. And it really demonstrated the power. But what was clearly needed was more expressive programming languages, because writing this software was still error-prone and time-consuming. The first compiler is credited to Grace Hopper. Grace Hopper deserves a lecture on her own, I think, from somebody, because she was a remarkable, feisty woman. I heard her lecture once, and she told some remarkable stories about how she had to go and steal furniture in order to get her first office underway when she was a captain in the US Navy, so she certainly knew how to make things happen, and she was a powerful force later in the development of COBOL, the business programming language. The higher level languages were needed to make programming easier and less error-prone. Fortran was developed primarily for calculations, for mathematical things, formula translation, Fortran. And the first compiler for IBM was a substantial piece of work, 17 person-years of effort developing a compiler for the Fortran language. But Fortran was spectacularly successful, still in use today, of course, very widely still in use. I mean, the Met Office weather forecasting, I believe, is largely still written in Fortran. And a terrifically useful language from that point of view, but a very primitive language from a software engineering perspective, because it didn't have most of the features you would need in order to be able to write programs that were well structured and where you could actually reason about the way that they behaved. ALGOL was developed, the algorithmic language ALGOL, arguably the most influential programming language that there has ever been. Tony Hoare famously said that ALGOL was a great advance on its predecessors and on most of its successors. And he's right. I mean, it is a beautiful language, and if you appreciate these things, get hold of a copy of what's called the revised report on ALGOL 60, the Bible of ALGOL. It's a very brief document. It defines the syntax of the language using Bacchus-Naur notation, the BNF, which is very easy to read and to understand. And it is an absolutely beautiful document describing an absolutely beautiful language. And ALGOL introduced some important features, in particular recursion, the ability of a procedure, of a subroutine to call itself. And therefore, of course, it created the requirement for stacks to be generated by the compilers and for a lot of interesting developments in compilation. But recursion enabled some really important algorithms to be written in a very succinct, very correct way. Tony Hoare credits Algol 60, for example, for enabling him to express the most important sorting algorithm that has ever been produced, quicksort, in a really succinct form. It enabled him to see how it could be done properly as an implementation of this algorithm that he dreamt up but couldn't quite see how to express in the most convenient way. And in the 1960s, while these things were happening, there was real advances going on in computer science. The underlying ability to define languages effectively, to be able to reason about languages, and to be able to analyze programs, the fundamentals for that were being put in place. And that gave us the start of being able to do proper programming and proper engineering approaches to developing programs. So we got software engineering, and we got the first software crisis. I'm going to talk about 3 of them. They come around about every 20 years. This was 20 years into the birth of, after the birth of computing. 20 years of history have passed. We've got to the mid-late 1960s. And large software systems were needed. The operating system for the new range of IBM computers, the 360 range, OS 360, it was a huge effort. $50 million a year during development. More than 5,000 person years of effort, and it was 2 years late. And it was by no means alone. Lots of big systems were overrunning. There was a software crisis. It was recognized, talked about. The NATO Science Council decided to get some experts together to discuss what the problem was. The conferences were written up. One of the editors for both of the 2 conferences that were organized was Brian Randall. And he's fortunately made the transcripts of those conferences, the write-ups of those conferences, available online. There's the URL. It's also listed in the transcript that you'll pick up when you leave if you want it. So you can download the PDFs. They're well worth reading. And they were full of insights that are still true today. A view from Larry of IBM that any significant advance in programming is going to involve automated analysis of programs. It requires a programming language which is susceptible to analysis. Hoare and Dijkstra talking about testing, saying essentially what I was saying so many decades later at the first of these lectures and my previous lecture here. But those things were ignored. The insights that came out of those software engineering conferences did not influence industry. And just as an aside, I want to mention it was just at around this time that Unix was first appearing. And there's details of how Unix came about in the transcript that I've written, but I don't have time to go into it now. But again, if you're really interested in programming or in Unix, find the original sources which are online and download them and read them. It's beautiful. It is a wonderful, wonderful architecture and a beautiful piece of programming. It's lovely stuff. So by the 1970s, we'd got the scientific foundations for software engineering. Work was going on in IBM of a mathematically formal definition in VDM of their programming language, PL1. Dijkstra had introduced structured programming, building on a theory of Jacobi and Bohm that showed that you didn't need lots of different ways of building programs, that you could do it with a very simple set of constructs. You didn't need gotos in particular, which was a big topic at the time. Tony Hoare had published an axiomatic basis for computer programming. He'd introducing the practical use of work, building on a lot of things that had gone before, but but introducing the practical basis for using preconditions, postconditions, invariants, and formal proof to really be able to develop software in a way that you could prove met your intentions. And also, object-oriented programming had been developed long before C++ ever appeared. Back in 1967 in the simulation language Simula. There's a terrific book, Structured Programming, Dahl, Dijkstra and Hoare, Academic Press 1972, that contains 3 short chapters, hugely influential papers, well worth reading still. In the 1970s, there was quite a lot of progress in the processes of software engineering. Stepwise refinement, the notion that you could define something at an abstract level and refine it step by step until you actually ended up with a real program, with each step able to show that it was consistent, that it really was still developing what you had said you wanted when you wrote down your abstract specification. Data-led design appeared. Again, very influentially, Michael Jackson introduced Jackson structured programming because he'd spotted that business computing was essentially taking data and transforming it into other data. It was reading in large files of data and producing typically reports or output files, and that the structure of the data should drive the structure of the program. So he was essentially teaching business programmers, writing in COBOL, to write what were essentially parsers, essentially compilers, transforming one grammar into another and writing and generating business programs that were structured that way. Practical formal methods appeared. And VDM was one of the most influential of those. Cliff Jones, who is the leader of the VDM, the developer of VDM, is in fact sitting in the front row here. So if you've got any hard questions about formal methods, he's the man to ask after I finish speaking. And there were advances in software development processes. People were starting to learn from the experience of some of the big systems. Fred Brooks, who had led the OS 360 development, published the Mythical Man Month, which is again, still well worth reading. Harlan Mills wrote a lot about the experiences that had come out of IBM, and his writings are again worth tracking down and reading. And Barry Beam of TRW did a huge analysis of lots and lots and lots of typically military system developments, and was able to produce lots of models to enable people to do a much more systematic job about estimating the time and cost of developing complex software systems. Again, very influential. We had the basis for professional software engineering, but most programmers still saw software development as a craft. Informal methods were widely promoted because there was a market for anybody who had a view as to how you could develop software better, because people found it hard. And EDSAC Dijkstra, in characteristic style, announced that essentially if you didn't program formally, then you were always going to be in crisis, and that you would end up with an incurable disease, and you'd end up inviting in the charlatans, and they would take the form of software engineering gurus. And there were a lot of software engineering gurus around. But of course, Moore's law was still operative, and it led to the second software crisis. Cheap personal computers had driven software and computing into many, many more application areas. There weren't good tools available for the processors that were being used and for the systems that were being built. We needed lots more programmers, and there weren't enough around who had the right background and training. And because all these new applications were opening up, there was a real rush to be first to market. And the driver for software development was who could get there first. and capture the market. Quality was very far down the chain of the drivers at that point. Inevitably, there were lots more failures. In particular, there were some very big government system failures, particularly in America. The Department of Defense decided it had to find out which of its contractors were actually capable of developing software in a reliable way, because they were having such bad successes, such big failures. So they set up the Software Engineering Institute at Carnegie Mellon University and asked them to come up with a way of assessing competence. They devised the capability maturity model. This is the start of the first real paper on it. Those are the main developers. And the capability maturity model essentially was a way of assessing the software development capability of a company into 5 levels. The level 1 was chaotic. You couldn't even do something right again if you'd managed to get it right before. Level 2 was repeatable. If you knew how to do something, there was a decent chance you'd be able to do it again reasonably well. Level 3 was defined, so now you've got a company standard, you trained your programmers in it, and most of them were actually following the standard. That's the sort of level that a professional implementation of ISO 9000 quality management gets you to. Beyond that, you're doing measurement and you're doing optimization of your processes. When they did the assessment, most defense contractors were found to be at level 1. Their processes were chaotic. And DoD then lent on a lot of them to move up the chain, which they managed to do. But of course, an awful lot of that movement was essentially gaming the questionnaires, and the value of being at the higher levels was essentially eroded and gradually became worth rather less. But the capability maturity model has been kept up to date, and there are various versions of it around now, and it's still doing extremely good work. In the UK, the government set up a program called STARTS, which I don't have time to go into. They started insisting on ISO 9000 quality management in some contracts, and that led most software houses in the UK to get certified against ISO 9000, which was a big step forward. At least they were now doing some formal quality management. There was, unfortunately, still a big focus on structured methods. A few companies started using formal methods, very, very few, but most companies were perfectly happy to carry on with informal specifications, informal designs, and because the specifications were obscure and incorrect and incomplete and contradictory, as informal specifications always are, of course there were then change requests when things were found not actually to be implementable or not to make sense. And companies started making money out of those change requests. They would bid a low price to win the business and then get their margins back on the changes. Essentially, it was fraud against the customers. But the good companies, those who actually did the work of really understanding the problem and producing good specifications and accurate estimates, didn't win the business because they were never price competitive against the people who were playing the other game. So the software industry got itself a very bad reputation, justifiably so, and the good companies weren't able to prosper. 1995, the Standish Group in America surveyed 8,000 plus application projects and published a report they called the CHAOS report. 31% of those projects were cancelled before delivery. Only 16.2% were on time, on budget, and met the requirements. All the ones in between hadn't been cancelled, but were either late, over budget, or didn't meet the requirements. And of course, the ones that were succeeding were typically the small, simple projects for small companies. For every 100 projects that started, there were 94 restarts. Many projects restarted several times, wasting time and money, of course. The average cost overrun, nearly 200%. The average time overrun, more than 200%. The average number of features delivered, about 2/3 of those specified. And while all that was happening, there was exponential growth going on in the internet. The internet, remember, is a network of networks. And each network typically has a lot of computers on it. And by the time we got to the mid-90s, hundreds of networks were joining the internet every week. The number of computers on the internet was growing enormously. And then Tim Berners-Lee introduced the World Wide Web, and companies woke up to the potential that there was commercially. And again, we got an explosion of applications, a real drive to do more with computing. And Moore's law was still making this possible and cost-effective. I don't have time to talk about the comms developments now, but if there are particular things in that timeline that you'd like more information on, ask about it on the website and I'll dig up the appropriate references for you. Quite a lot of lessons were learnt at the craft level during the 1990s. And out of that came a lot of the agile methods that are now around. And they overcame some of the problems that were being faced because people were learning from experience. Crafts do learn from experience. But the methods turned out not to work very well on big complex problems or novel problems. And by the time we got into this century, the year 2000 came and went. And I think I will talk in another lecture about the Y2K problem and about whether it was a scam, as people often think, or whether it was actually a very near miss for Western civilization. I was running the year 2000 services for Deloitte Consulting worldwide in the mid-90s. And I mean, some of the things that we saw and had to get fixed would make your hair stand on end. I mean, if we hadn't fixed literally tens of thousands of problems in systems, an awful lot of things would have failed. And in any case, a lot of things did fail. And a lot of businesses went bust as a consequence, and there was quite a lot of trouble, most of which never actually made the press. But there's some good stories to tell about that. And interestingly, the lessons haven't yet been learned from getting so close to a major problem. The things that enabled us to avoid the forecast disaster haven't actually led to fundamental changes in the way that we do things, and therefore the potential for another Y2K scale disaster is actually still around. So there's potentially something to talk about there. I mean, if you're interested in a lecture on that, then let me know and I'll see what I can do. But even now, you see, almost all software developed without a rigorous specification. Almost all verification and validation done by running tests, and we've seen how long we've known that is not a satisfactory way of establishing any high degree of competence in important software. And now, because of the Moore's law generating this new wave of mobile devices, of smartphones and connected vehicles and the Internet of everything, suddenly we've got a new wave of problems. We've got many, many, many more programmers, again, with little experience, because not having lived through some of the learning that has happened during the history of computing, and very often without any formal training in computing, writing software that, if not actually critical in its application, a particular app on a smartphone may be just a game. It may not matter at all if it fails. But if it makes everything else on that device vulnerable to a cyber attack, then suddenly it's a real problem. And most of the people writing software for those devices have really no understanding of computer security. It's an interesting and well-researched and well-understood subject now, and you need really quite a lot of background in order to be able to do secure software effectively. How many programmers am I talking about? Well, here's one estimate for 2004 that I found, and they reckon 18 million more worldwide. I'd say that was an underestimate. I don't think they've picked up an awful lot of people working inside companies doing things that aren't recognised as formal software development, but which really are. But nevertheless, that's a huge number of people, and it's far more people than have ever gone through any formal training to develop software. So where are we? We've got the third software crisis. Hardware is mostly well-engineered and reliable because that's been their business priority. That's how you made money as a hardware developer. If you weren't doing good engineering, you weren't going to be commercially successful for very long. But software's had other priorities. If you focused on quality as a software developer, you didn't get rich. There were very few application areas where that really was the deciding factor that enabled you to win the business, to do the development, to sell your products. For most of the market, getting functionality out into the market and getting the customers to be your test bed, to tell you about the flaws, and then selling them a maintenance contract quite often in order to fix the errors that you'd made. That was the way you made money. And so, not surprisingly, software is not yet well engineered. But that's fine for the vast amount of software that at some level doesn't matter. But when we start talking about maybe moving to a cashless society, and therefore becoming completely dependent on computer systems for day-to-day transactions, travelling on transport, buying food, not having a fallback if the banking systems don't work. And of course, within the last few weeks, people have been locked out of their banking systems on several occasions because of failures in banking IT systems. And we've got cyber attacks. The government risk register rates the threat from cyber attacks as a threat that's as great as war, terrorism, or pandemic infections on the scale of Ebola or pandemic flu. It's up there as a tier 1 threat on the National Risk Register. So are we being complacent in not tackling this software crisis? Because I see it as a real crisis. How did it happen? Well, I leave it to Tony Hoare. It seems highly appropriate. The livery company for the barber surgeons is just down the road from here. And he expresses it absolutely brilliantly. That's really why the word from the academics has been ignored. And the customers, unfortunately, have been seduced by functionality at low prices and hang the consequences, and willing to sign up to the sales terms that mean that when things do go wrong, the developers don't appear to have any liability. So please join in the discussions. Thank you very much. I've managed to finish with time for questions, for which I almost deserve a round of applause, given what happened last time.